Hi everyone, in this video we're going to be looking at the basic principles and some examples to do with simple harmonic motion. So this idea of an object being in simple harmonic motion, like weights on the end of springs, there's all kinds of examples, bridges, planes that undergo this simple harmonic motion. It really is just a particular kind of differential equation that we're solving. And the solution of that differential equation you'll see is trigonometric functions. So if you think about a pendulum or a spring going back and forward, it wouldn't surprise us that the motion is periodic and it follows a trigonometric form. So the particular kind of differential equation is this one here, where the second derivative is equal to negative k squared times the actual value of the function. I'm going to get into that more in a second. You see that in the syllabus it says there's three kinds of solutions to that differential equation, and they're all basically, if you do the second root of all of those, it will fit that equation that we have right here. So a lot of these we use x instead of y. I know in the syllabus here it's talking about y, but a lot of the times we use x for the displacement from a center point. So we're talking about rectilinear motion, so we've got a middle point here, and we're just going to say x is a certain distance away from that middle point. What this differential equation says is that the acceleration, that is the second derivative there, the acceleration of the object, the rate of change of the velocity, is equal to a constant, and we write it like this for good reason, you'll see in an example, is equal to a constant times the distance the object is away from that central point. So the further away you are, the greater the acceleration of the object. Let's do some calculus now to actually work out the equations. Again, you can skip through this if you want to just get to the bare bones of the actual examples, but I think it's good to know where we get these equations from. So we want to solve this differential equation, which is x dot dot. This is really getting back to Newton's notation here. That's shorthand for the rate, or the second derivative there, that we'd write like that. So I might use that notation because it just saves some time, but it is important to use the derivatives as well. So here we've got dv dt, the rate of change of the velocity is negative k squared x. Okay, so v is the velocity, the second derivative is the acceleration, so here we've got dv dt. Now writing it like this is going to help us. Now this is a little trick here. So this is using the chain rule. I can write the left hand side like that, just to confirm. Those would kind of cancel, leaving me with dv dt. So I've got dv dx times dx dt on that side there. So now dx dt is just v. This is just the velocity. So I've got dv dx times v is equal to negative k squared times x. Alright, now we're going to separate the variables and integrate here. So I'm going to leave the v over there with the dv, negative k squared x dx. Okay, so over on the left hand side we've got v squared over 2. Over here we've got negative k squared x squared over 2 plus c. Okay, but the amplitude, and we normally say the amplitude is A, so the range of the motion here, so when x is equal to A, v is equal to 0. So we get as far out, as far away from the center point as we can. When the acceleration is maximum, the velocity is going to be 0. So that therefore means that 0 is equal to negative k squared a squared over 2 plus c. So c is k squared a squared over 2. So we get v squared over 2 is equal to negative k squared x squared over 2 plus k squared a squared over 2. Now remember here that a is the amplitude. It's the biggest value you're going to get for x. So if we times everything by 2 and do a bit of factorising, we get k squared a squared minus x squared. That's probably the nicest way to write that. And there's an expression now for the velocity in terms of k, which is a constant, which you will find working these problems out. A is the amplitude of the motion, and x is the distance that the particle is away from the center point. So that's an important equation to know. Now we can, I guess, take the square root of that. Let me start up over here. We can say v is taking the square root of both sides, root a squared minus x squared. When we're trying to solve this differential equation, so we're trying to get x on its own. So v, the velocity, is just the rate of change of the displacement. And this is an integral now that we need a bit of substitution to help us do. First, let's separate the variables. So we've got 1 over root a squared minus x squared dx, and over here we've got k dt. So I've separated the variables. Now we can use the substitution a sine of u. I'm not going to go through the whole details here, but you get dx du is equal to a cos u. You can see if you substitute in a sine u, you've got a squared minus a squared sine squared u. The a squareds will come out and you'll have 1 minus sine squared, so you'll end up with root a squared cos squared on the bottom, which is just a cos u on the bottom. With replace the dx with a cos u du. See, everything cancels out nicely and you just end up with this. I did that very quickly. You might want to do that as an exercise. So that just gives you u equals kt plus c. And sometimes we use alpha, but yeah, a lot of the times I think I'm going to be using alpha, so I'll use alpha there. So remember u. So therefore u was, our x was equal to a sine of u. So that means x is equal to a sine kt plus alpha. So that shows you that one of the solutions of this initial differential equation is this trigonometric function here. Remember, where a is the amplitude of the motion, we can see that there. K is going to affect the period, and alpha is what we call a phase shift. So it's going back and forward, left and right.